Okay, today we will see the continuation of water technology. Today we are going to see determination of hardness of water by complexometric method or by EDTA method. What is a complex? Complex is also called coordination compound. You can say inorganic complex or inorganic coordination compounds. Okay, coordination compounds. So what is a complex or coordination compound? So okay, let us take one example to explain this. K4 FeCN6. So we know that this type of this is called potassium ferrocyanide. Okay, potassium ferrocyanide 2. Potassium. Okay, 1 minute. It is generally called potassium ferrocyanide. In IUPAC name is potassium hexacyano iron 2. Okay. So in this, we know that this is it's an example of coordination compound. The iron is a central metal atom. 6-cyanide ligand. 6-cyanide, or we call it as ligand, 6 ligands. Okay. This is counter ion. Okay. This is called a coordination compound. Where here the ligands, for example, cyanide is a negative ligand. Okay, is a monodentate ligand. What is meant by dentate? Means one of the atom go and bind with the central metal atom. For example, nitrogen here. So if you see the structure of this, minus through the negative, this is the structure of the complex. So ligand donate electrons through its negative charge or lone pair. For example, ammonia ligand through lone pair. Here negative charge. So central metal atom accepts those electrons and they are called Lewis acid. And ligands through their negative charge or through lone pair donate the electrons to central metal atom. So they are called Lewis base. So, and they form a coordinate covalent bond, not a covalent bond, coordinate covalent bond. So this is a coordinate covalent bond. Okay. Okay. So like this, metal and ligand bind to form a coordinate covalent bond. We call it as coordination compounds. Okay, and also called inorganic complex or inorganic coordination compound. What is special about this complexes in solution? For example, KCl salt you take in aqueous solution, it will be K plus Cl minus. Okay. Or even if you take potash alum, it's a mixed salt like K2O. It's a mixed salt. Then they also have ions like K plus, calcium 2 plus, oxide 2 minus, Si 4 plus, like that. Now you take any inorganic complex or coordination compound like this, it will be like 4 K plus and FeCN6 4 minus. So this will retain its identity in the aqueous solution. That's why we put in the square bracket while writing. Okay. So that is the speciality of complex ions. So if this FeCN6 will not further split into Fe2 plus and 6Cn minus. It will remain as FeCN6 4 minus in aqueous solution. That is the special about complexes in solution. Okay. What is chelate effect? What is chelate effect? Okay. You have, for example, monodentate ligand. Only through ammonia it can bind to the metal. Sorry, nitrogen in ammonia it can bind to the metal. Cn minus. Again, this is monodentate ligand means it can bind through only one atom, either through negative charge or through lone pair in that atom. Okay. OH minus aqua ligand. Okay. So these are all monodentate. Now, when you come to bidentate, means two atoms can go and bind with the central metal atom and form coordinate covalent bond. So they are called bidentate. Dentate means it's like biting the metal atom. Ligand go and bite the metal atom. That's why this dentate name has come. Here denticity means how many such atoms can go and bind. Denticity is 1. Here denticity is 2, like that. Okay. Bidentate means oxalate ion. Okay. Glycinate ion. Okay. And you have lot of other examples. For example, ethylene diamine. Ethylene diamine. So these are all examples of bidentate where they can go and bind the metal atom. For example, En. This is called ethylene diamine. En can bind through both nitrogen lone pairs. So it can bind like this. Can bind like this, or several other ways of binding. For example, it can also bind like this. Binding means nitrogen lone pair goes and form a coordinate covalent bond with metal, central metal atom. So this is bidentate. So when you have compared to monodentate, when you have bidentate, for example, metal oxalate. Okay, oxalate, bidentate. Oxalate, ethylene diamine, glycinate. Okay, all these things, bidentate ligand, when they form a ring structure in the complex. So they are highly stable thermodynamically compared to monodentate, that like only monodentate with ammonia, aqua ligand, okay, cyanide, okay, cyanide, like that. These are all monodentate. So this compared to monodentate forming a complex with metal and bidentate forming a complex with metal and higher multidentates forming a complex with metals, there are a lot of differences in their stability. So compared to monodentate, bidentate form a ring, and bidentate and multidentate further 3, 4, 5, 6. Bidentate means 2 atoms, 3 atoms tridentate, 4 atoms from the same ligand, we call it as tetradentate, 6 atoms from the same ligand, we call it as hexadentate, like that. So all these multidentates ligand containing complex have thermodynamically more stable. They have a very high equilibrium constant compared to the monodentate containing complexes. So when this type of ligands form a complex with metal, we call it as chelate complex, chelate complex or chelate complex, chelate complex or chelate complex. The effect of its more stability due to the ring formation it gives to the complex is called chelate effect. Okay, now we come to determination of hardness of water by complexometric method or by EDTA method. EDTA means ethylene diamine tetraacetic acid. Okay, or we can say acetate ion. How they will bind, like through the tetraacetate. What is the denticity of this ligand? 2 lone pairs nitrogen and 4 O minus. So 4 oxide, 4 O minus atoms and 2 nitrogen lone pairs can form a hexadentate, form a bind with metal. So it's a hexadentate ligand. A very good chelating ligand used in water chemistry. Okay. So this is the structure of ethylene diamine tetraacetic acid. This is the ethylene diamine tetraacetate. It forms 4 minus. Okay. So we call it as, normally we call this as H4Y. We call this as Y4 minus because H's atoms are removed. Okay. Okay. So now this ligand is used very well in, it's a very well known ligand in chemistry and also particularly in water chemistry because it binds with calcium and magnesium, which is ions which are major reasons for hardness of water. So now we'll move to complexometric. Okay. Okay. For example, again, hexadentate EDTA ligand we have seen can form chelate, ring formation, most stable. Complex with many metals, not only calcium and magnesium. Since it is water technology, we are interested in calcium and magnesium ions. It can form with EDTA is a very good complexing agent. Very good complexing ligand or agent. It can bind with, it can form complexation with many metals. That's why we put common. Here metal can be transition metal or any transition metal or main group metal or alkaline earth. Alkaline earth, calcium, magnesium is what we are interested. Okay. Because of water technology, we are interested in. So this is an example of metal octahedral complex. How one ligand, one EDTA ligand can form this much this complex, 6 atoms. Like for example, we have shown in the previous slide, 4 oxygen atoms from 4 acetate ions, oxide O minus ions from oxide acetate ions, and lone pairs from nitrogen can bind with central metal atoms. So it's a hexadentate ligand. That's why we call it as hexadentate. 6 atoms on the single ligand is binding with the metal. Okay. And if you see, there is a 5-membered rings. Okay. 1, 2, 3, 4, 5. 5-membered rings. Like that, it is forming a strong ring formation, and that's the reason it is highly stable and have a very high equilibrium constant compared to monodentate ligands. Okay. Next. Okay, what is the principle of this complexometric titration? Since we are using EDTA and EDTA binds with calcium 2+ ions and magnesium 2 plus ions in hard water. We call this method as complexometric method or EDTA method or complexometric titration, which is by titration basically. So the titration is called complexometric titration, where calcium EDTA or magnesium EDTA complexes are formed. What is the principle behind this? Calcium, magnesium ions present in water are responsible for hardness. We have seen already and we know this. This ions forms less stable complex with the indicator. In this titration, we use the indicator Aeronautical black tea. This is the structure of Aeronautical black tea. So it's a diazo compound. This diazo, basically it's a dye. Okay, diazo dye. Okay, this is the reason for it brings color. Indicator, why we use indicator? Because it gives it gives a particular color at the end point so that the end point can be determined with perfection. So EBT, Aeronautical black tea indicator is used in this complexometric titration, and when you add Aeronautical black tea at pH 10, okay, the metal, calcium and magnesium reacts with EBT indicator and forms a less stable complex at pH 10. pH 10 is maintained by adding buffer. Maintained by adding ammonium chloride buffer solution. So that pH 10 is maintained. At pH 10, it forms a characteristic wine red color. Okay, that is due to the formation of metal, calcium, magnesium. Metal here means calcium and magnesium. Okay, with indicator IN or EBT. Okay, basically, when calcium or magnesium forms a complexation with EBT, it is wine red color and less stable. Whereas it forms a stable complex, okay, stable, very highly stable complex with EDTA. Okay, that's why we are using this as a fact to estimate the hardness of water sample. It forms a weak, less stable complex with indicator, whereas a strong, highly stable complex with EDTA. Okay. So indicator used in this is EBT. When EBT forms a complex with metal, according to this reaction, it will be wine red in color at pH 10. So when water gives wine red color with Aeronautical black tea indicator at pH 10, then it's a confirmation that the water is hard water. Only if calcium, magnesium ions are present in excess, and when you call that hard water, this red wine color will come. So this is the indication that water is a hard water. First, red wine color indication is a water we are using is hard water. It contains lot of magnesium and calcium ions. Hardness is there more. Okay. So when we add, so this is a titration type. We call it as complexometric titration. So we have this red wine color, which is due to metal EBT indicator complexation, okay, which is very weak, okay, not very weak, unstable. So when you add EDTA, from burette to this solution, it changes to blue color. This is the end point where all EDTA combines with metal and EBT is released. Okay, This blue color is due to indicator. The complex is colorless. Okay, calcium EDTA or magnesium EDTA complex is colorless. Okay, but what comes out when all EDTA, when all metal ions forms a strong bond with calcium and magnesium ions, then it releases the indicator as a free solution. That's why it is blue in color, due to the indicator, not because of the color of the complex. Here the color of the complex comes from calcium magnesium ion forming complexation with indicator, whereas here it is due to the free indicator, not because of the complexation. Color doesn't come from the complexation. Okay, whenever we are adding EDTA solution to the wine red color, this is wine red color, metal indicator complex. The metal ions form more stable complex with EDTA. So wine red color, EBT complex with calcium magnesium. When you add EDTA, it becomes, the EDTA will go and bind because it is thermodynamically stable chelate structure it forms. So what happens when all EDTA is binded with calcium or magnesium, then EBT is released. That is the end point. So at the end point, we get blue color solution, that is due to indicator color. Okay, we call it steel blue color or blue color. So EBT is blue in color, whereas the complex is calcium or magnesium ion forming complex with EDTA is colorless. Okay, so this is done at again pH 10, which is maintained by a buffer solution. Okay, ammonia, ammonium chloride buffer solution. When all the metal ions in the sample, metal ions here means calcium and magnesium. When all the metal ions complexed with EDTA, further addition of EDTA liberates the free solution at pH 10, which is blue in color. That indicates the end point of titration. Okay, so this is the principle behind complexometric titration to find the total hardness or permanent hardness of water. Okay, so this is the complex. This is the chelate complex formed by calcium, or we can say magnesium EDTA. Instead of calcium, we can put magnesium also. Okay, this can be magnesium. Central, here we are seeing the calcium. Central metal atom is calcium, and acetate ions, 4 O minus ions, okay, from acetate, and two lone pairs from nitrogen. They form a bond, covalent coordinate bond with central metal atom. Okay, that's why it is forming a octahedral. Why we say it's an octahedral complex? Because there are 6 atoms. There are 6 coordination number, means it's surrounded by 1, 2, 3, 4, 5, 6. So calcium, coordination number of calcium is 6 here. That's why it forms a octahedral complex. Okay. So this is very, very stable, thermodynamically highly stable ligand. Okay. Okay, now determination of hardness of water by complexometric, or we can also say by EDTA method. So there are various steps involved in this method. First, preparation of required solutions, standardization of EDTA solution, determination of total hardness, and determination of permanent hardness. When we determine these two, then temporary hardness is nothing but total minus permanent hardness. Total hardness minus permanent hardness gives you the value of temporary hardness. Okay. Okay. Now, what are the preparation? What are the solution required? EDTA salt solution. Disodium salt of EDTA. Why we use disodium? Why we use disodium salt and not EDTA directly? Because the solubility of disodium salt of EDTA, solubility in water, is good compared to direct usage of EDTA. When you use directly EDTA, solubility is not that much good, but when you use disodium salt of EDTA, it is having a good soluble nature in water. So that's why we use the salt of EDTA, not the EDTA directly. Okay. Okay, this is the one of the preparation. And then standard hard water. You have to take 1 gram calcium carbonate, few drops HCl, 1 liter of distilled water. Then EBT indicator. Okay, we have seen in the principle what is the role of EBT indicator in 100 ml alcohol. Buffer solution also we have to add, because we have to maintain. Buffer solution is used to maintain pH 10. So at this pH only, this wine red color formation is there. So we have to maintain this pH 10 throughout this experiments, throughout this titrations. For different stages, different steps, we have to maintain it fully at pH 10. So we need to add buffer solution, which is ammonia, ammonium chloride buffer solution. Okay. So this is with respect to preparation of solutions. Next step. So first step is preparation of solution. Second step is standardization of EDTA salt solution. EDTA salt of disodium salt of EDTA solution. So we will take the EDTA salt solution in burette. A conical flask, we will take 20 ml of standard hard water, which we prepared by calcium carbonate and by adding food. Okay, calcium carbonate. We prepared the standard hard water as seen in the preparation of solutions. So that we have to take in a conical flask. So normally burette. Okay. In the titration we use burette, and then which will be having a conical flask. Okay. This we say burette. This we say conical flask. What is meant by standardization? Standardization means we have to find the strength of this EDTA salt solution. Okay. What is meant by standard solution? Standard solution means whose strength is known, accurately known. Okay. Standard solution are made with a standard measuring flask. For example, 100 ml, we have a mark here. So it's standard measuring flask. Or we can also say volumetric flask. Okay. Okay. Conical flask, pipette out. Pipette pipette will be something like this. Okay. This is also open. This is like this. We will draw. Okay. Okay. Pipette will not be exactly like this. I will tell you. I will draw in a neater way. Pipette will be. Okay. This is a pipette. So we have to pipette out 20 ml of standard hard water which we prepare. Concentration M1, strength M1. Indicator we know 5 ml of buffer solution and EBT indicator 3 drops, which forms a wine red color. End point is 2. You have to titrate the solution with EDTA. Still we get blue color. So we have seen the this thing. So this is the after adding indicator with buffer solution, we get wine red color. We have to titrate with burette, EDTA, disodium salt of EDTA solution from the burette. Still, we get blue. At the moment, blue color comes. Okay, we have to stop. This is the end point of titration. Okay. So, we have to do the titration. Still, blue color appears. Okay, let the volume of burette be volume of the burette used be X. Okay, this is M1V1. This is the volumetric analysis formula. M1V1 is equal to M2V2. M1 is the we know molarity of standard hard water 0.01 molar. V1 we know volume of standard hard water taken 20 ml. M2 is molarity of EDTA. V2 is volume of EDTA. From the titration we know. From this we can calculate M2. M2 can be calculated. M2 is nothing but strength of EDTA. So we are determining the strength of EDTA. That's why we call it as standardization of EDTA. Okay, EDTA salt solution. Okay, next this is over. Next is third step, determination of total hardness. So burette again, this is now standardized. Okay, standard EDTA solution whose strength is determined already in the second step. Conical flask, sample water, any water whose hardness has to be determined. We call it as sample water. Okay. So indicator same. Buffers ammonium chloride buffer 5 ml, 3 drops of EBT indicator. End point again wine red to blue color. So let volume of EDTA from the burette be YML. And now here M2V2 is equal to M3V3. M2 is already determined here. Molarity of EDTA. V2 is volume of EDTA. From this titration we will come to know. M3 is the molarity of sample water which we need to determine. V3 is the volume of sample water taken. We know that 20 ml. So from this molarity is calculated. Molarity of strength of sample water. Molarity of sample water is calculated from this step. So now this is the molarity, the strength of this sample water gives the strength of total hardness present in water. Okay. So M3 into molecular weight of calcium carbonate 100 into 1 liter. M3 into 10 power 5 ppm. That is the milligram per liter of total hardness. Okay. Total hardness in milligram per liter. This whatever we get here. For example, okay. For example, if M3 is equal to 0.00059. Okay. Okay. 0.0059. Then the total hardness in ppm or milligram per liter is equal to into 10 power 5, 1, 2, 3, 4, 5, 590 ppm. This is how we calculate the total hardness. Okay, let's have this here. Next step, determination of permanent hardness. So what is permanent hardness? If you, for example, the sample water which we are using to determine the hardness, sample water which we used in the previous step. Take 100 ml of sample water, okay, boil it. If you boil, cool, and then filter, we get a water removed for carbonate hardness. So what happens when you heat boiling water? Calcium present in it will precipitate as calcium carbonate. Magnesium ions present in it in the form of calcium bicarbonate. See, temporary hardness can be only in the form of bicarbonates. Okay. Temporary hardness means we call it as, normally it will be present as bicarbonate. So when you heat it, it becomes calcium carbonate precipitate out or magnesium hydroxide precipitate out. So temporary hardness is removed by this after filtration. So what remain in this sample water after boiling the water is permanent hardness. Okay. Okay. So boil it to remove the temporary hardness and cool. Okay. Make up the volume of original water by distilled water. So this makeup up to the volume we will do in standard measuring flask or volumetric flask, which I told in the previous slide. Okay. Burette solution again is a standard, which is already standardized, standard EDTA solution whose strength is known. A conical flask, we put out 20 ml of the above filtered water, which is V4. Okay. 5 ml of buffer solution, 3 drops of EBT, we get wine red color. Titrate with EDTA solution, still we get blue color. When blue color comes, you have to stop the titration because that is the end point. Okay. So now what, let the volume of EDTA consumed from the burette be XML. Okay. Now M2V2 is equal to M4V4. M2 we know molarity of EDTA, which is known, strength is known. V2 is volume of EDTA, ZML from this titration. M4 is molarity of permanent hard water, which we have to find out from the experiment, from this step. V4 is we known, 20 ml, which we are taking. Okay. So whatever we get, M4 is the strength of permanent hardness. Okay. For example, if it is 0.0028 molar, then permanent hardness in terms of ppm is 0.028 into 10 power 5 is equal to 280 ppm. That is the permanent hardness. Okay. Okay. Now, from this total and permanent hardness, how much we get? Temporary hardness, I will have 590 minus 280. 590 ppm is the total hardness, for example, we have shown. So here for temporary hardness, for example, 590 ppm minus 280 ppm, which is equal to 310 ppm. This is the temporary hardness in ppm. Okay. So this is how the titration is done, and the hardness, temporary, total and permanent hardness is determined. Few more problems if we do in the numericals we do in the problem video, then we can be more understandable. Okay. Okay. With this video is over. See you in the next video with more from water technology.
Like, share and subscribe. Hit the bell icon for more updates.